Today we're going to start any physics problem. We always want to check units and see if there's anything we need to convert. Now looking at all of these, I have kilograms, that's good. Meters per second, also good. Over here, meters per second is good. But here, the football is in grams. So the first step that I'm going to need to do is I'm going to convert that grams to kilograms. Since this is a metric to metric conversion, I can use the King Henry died drinking chocolate milk. And what's going to go in this empty space is grams, a G, because I'm talking about a mass. Okay, so I'm starting with that 410 grams from here, and I'm going to convert it to kilograms. So to do that, I'm starting at the G, and I want to go to the K. So to get there, I'm moving the decimal point 1, 2, 3 times to the left. If there is no decimal point present, like in this number, you start at the end and you'll move the decimal 3 times to the left, just like I did up here. That is going to give me 0.410 kilograms. So this being the mass of the football in kilograms. So this is the value that I will be putting into my equations once I get to that step. So I'm going to go ahead and erase this section and make a list of my knowns and unknowns. So the mass of that football, so I'm going to do M sub B, mass of ball. That was 0.410 kilograms when we converted it. So the mass of the football here, the velocity of the football is 45. So velocity being the letter V, and I'm going to write V sub B because it's the velocity of the ball, 45 meters per second. So I'm just labeling these with a B since we're comparing two different momentums. That way I can keep track of which velocity belongs with which mass. So next, I'm going to look at the mass and the velocity of the football player. So the mass, so M sub P, mass of player, is going to be 110 kilograms. The velocity of the player is going to be 8 meters per second. And what I'm trying to solve for then is the momentum. And remember, momentum is represented by the letter P. Okay, so I'm going to use these values to figure out the momentum, the P, of the player. And I'll use these two values to figure out the momentum, P, of the ball. And then I'm going to compare, see which one has greater momentum. Because remember, momentum is dependent upon mass and velocity. So the equation I have for that would be then multiplying mass times velocity. So let's do the player first. So for the player, I'm going to take the 110 kilograms and I'm going to multiply it by the 8 meters per second, the velocity. Okay, and what that's going to give me is 880, and the units are just kilograms for the mass times meters per second for the velocity. Okay, so 880 kilograms times meters per second is the momentum of the football player. Now let's look at the ball. So the momentum of the ball is going to be the mass of the ball, which we got to be 4.410 kilograms, times the velocity of the ball, which is 45. So the velocity, the ball is going a lot faster than the player. So let's see what its momentum is. So multiplying those two, and we're looking at two significant figures. I'm going to get 18. So now comparing them, which has more momentum, the player or the ball? Well, no contest, right? 880 for the player and only 18 for the ball. So even though the player's going at a lower speed, a lower velocity, their mass gives them a lot of momentum. Okay, so the player is going to be have the higher momentum. This time we have a T-ball player hitting a 52.1 gram baseball off the tee at a velocity of 37. We have a contact time and we want to calculate impulse and force. Okay, so we're going to start by checking and seeing if we need to convert anything. Right away, the first piece of information I see is in grams. Do we want it in grams? We do not, so let's convert 52.1 grams to kilograms. So metric to metric once again. So the King Henry died drinking chocolate milk. Grams is our base. We are at the G and we want to get to the K, so we're going to move the decimal 3 times to the left, starting at the decimal point. 1, 2, 3. And what's going to go in that empty space? A 0. Okay, so we're going to get 0.0521 kilograms. All right, so let's erase this and do my knowns and unknowns. So that conversion I just did of 0.0521 kilograms, what variable is that? It's going to be a mass, an M. Next I have velocity of 37 meters per second, so velocity being the letter V. Contact time, so the time, letter T, is 2.1 times 10 to the negative 2 seconds. Okay, so this is a in scientific notation. So that negative 2 just means move the decimal point 2 to the left, make the number smaller, and you'll get this number here. So 0.021. You can also enter it in your calculator in scientific, and that'll work just fine as well. Now they want us to calculate the impulse and the force. All right, so if you remember impulse, it has 2 equations for it. Okay, so impulse is the change in momentum. So that's what this delta P means, change in momentum. Whenever you have the change in something, it's always final minus initial. So that's how we get the equation of mvf minus mvi. So this is one of the equations on your equation sheet. And notice mass times velocity, that is equal to momentum. So we're taking the final momentum, that's what that sub f means, and we're going to subtract it from the initial momentum to get our impulse, to get our change. Okay? The other equation we have is F times T. So looking at my knowns, which equation is going to be useful to me here to calculate impulse? It's not going to be that guy. Do I have mass? I do. Do I have a final and an initial velocity? Well, not at first glance, but let's think about this. So a T-ball player hits a ball off the tee. So that ball is initially just sitting on the tee, is initially at rest. So what is the initial velocity of that ball? The initial velocity of that ball is going to be 0 because it's just sitting on the tee. So I do have the initial velocity. My V sub I is going to be 0 because the ball is at rest. So this 37 meters per second, that is going to be my final. That's after the player hits the ball. Okay, so let's plug in. Now notice the mass, it's going to be the same in both spots because we're talking about the change in momentum of one object, in this case, the ball. So let's plug in what we have. So I have my mass of the ball is 0.0521 kilograms. My final velocity of the ball is 37. Now I'm going to subtract the mass of the ball, so same mass, and that is multiplied by the initial velocity, which is just 0. Okay, so notice I'm multiplying 0.0521 times 0. So what is anything multiplied by 0? It's going to equal 0. Okay, so all I need to do is multiply my mass and my final velocity to figure out what my impulse, what my change in momentum will be. So multiplying those two numbers, I get, how many sig figs are we looking at? Looks like 2. 1.9. Now for units on it, since impulse is equal to the change in momentum, change in P, the units are going to be the same as the units for momentum. If you ever forget, look at what you're multiplying. We multiplied mass. What is mass measured in? Kilograms. Times velocity. What is velocity measured in? Meters per second. So my impulse, my change in momentum of that ball is 1.9 kilograms times meters per second. Okay, so I've solved the impulse part of the problem. But I still need to solve now for force. And I know based off of chapter 5, you're initially going to want to look at those force equations, right? Force is equal to mass times acceleration, all that good stuff. But looking at this, I don't have acceleration. I have mass, but I don't have acceleration. So if you're ever solving a problem that's having you calculate impulse and force, look at all your impulse equations. Okay, we said one of them was this MVF that we just used minus MVI. So your final momentum minus your initial momentum. But the other impulse equation is force times time. So you can solve for force by rearranging this equation. We have impulse because we just solved for it, and we have time. So I'm going to rearrange this equation to solve for F. If I want F by itself, I need to get rid of the T. So the T is in the numerator. I'm multiplying by T. So I want to do the opposite. What that means is I want to divide by T because that's going to get rid of it. I have T over T, they cancel. Whatever I do to one side of the equation, I have to do the other. So since I divided by T on this side, I'm also going to divide by T on the other side. That's going to get me force by itself now, because the T's canceled, is equal to impulse divided by time. So now I can plug in force is equal to impulse 1.9, the time is 0.021. And we're still looking at two significant figures for our answer. So 1.9 divided by 0.021 is going to give me 90 on the dot. So I'm going to need a decimal point there. So 90, and I'm putting a decimal to make sure that 0 counts because I said two significant figures. Now what are the units on force? Same as it was in chapter 5, after good old Sir Isaac Newton. So 90 newtons of force was applied to that ball to get it to go 37 meters per second. Now we're going to look at a collision problem. And with collision problems, what's really happening is momentum is being transferred. Okay, so this one has two cars colliding and sticking together. The first car, 15 meters per second, given the mass as well. Second car was initially stopped. They want us to calculate the velocity of the cars after impact. Okay, so the first step is to go through, convert if necessary, and then after that, make your knowns and unknowns. All right, so conversions, looking at all the numbers present, I do not need to convert anything, so that step's already done. Okay, the first car, so I'm going to label it M1, and then V1. So that first car is 15 meters per second. So is that the mass or is that the velocity? Meters per second is your hint there. That is a velocity. Mass of that first car is 1750. Now the second car. So for the second car, we're going to have an M2 and a V2. The second car was stopped. So what is the second car's velocity? Second car's velocity is 0. It's stopped. It's not moving. Okay? And then the mass of the second car, 1650. What they want us to calculate is the velocity after the collision. So the final velocity after impact. Okay? Now to do a collision problem, you need to figure out what type of collision it is based off of those definitions we looked at in the PowerPoints. And there's two different types of collisions. One is inelastic, where two objects collide, stick together, and then move off together. The other one is elastic, where two objects collide and bounce off of each other and go their separate ways. So you have to look for clues in the word problem to figure out the type. Now, the clue here is that they stick together. So if they stick together, that means they're now one object moving in the same direction at the same velocity. Okay, so we're going to do inelastic because of the fact that they're sticking together. And the inelastic equation on your equation sheet looks like this. All right. Now let's look and see, make sure we have all the information. We have the mass of the first car, velocity of the first car. Yes. Mass of the first car, velocity of, or second car, sorry. Yes, we have both of those. Okay, so remember this side here, this is before collision. And this side over here is after. And what we're looking to solve for is the velocity after, this v sub f. So we're going to need that by itself. So if we want velocity by itself, we need to get rid of this m1 plus m2. So to do that, what we're doing here is we're taking this m1 plus m2 and we're multiplying it by vf. So to get rid of it, we're going to divide. So we're multiplying, so to get rid, we're going to do the opposite operation, which is division. So I'm going to divide m1 plus m2. That whole parenthesis, it's dividing by that. Because what that's going to do is it's going to get rid of it on this side. But since I divided by m1 plus m2 on the right side of the equation, I need to do the same thing on the left. So my equation to solve for the final velocity, I'm going to take the mass and velocity of both vehicles before the collision and divide it by just the masses after. So notice we add just the masses after the collision because the two objects are stuck together. So they're one object now. So that's why we can add their masses. So let's plug in. We have the mass of the first object, 1750, times the velocity of the first car, 15. We're going to add that to the mass and velocity of the second car. Now, the second car is initially not moving. So what is its momentum if it's not moving, if it's parked? Its momentum is going to be 0. If an object's not in motion, it can't have any momentum. And we see that right here. Taking 1650 times 0 is equal to 0. Okay? Simplifying that equation a little bit. On the bottom in that denominator, we're going to add the masses of both vehicles. So 1750 plus 1650. Make sure that this denominator here, this addition, is in parentheses when you enter it into your calculator. Okay, so we have 1750 times 15. We're going to divide that by 1750 plus 1650. Making sure to have that bottom portion in parentheses so it does the addition first. So what I get is 7.72 meters per second. Now let's look quickly at my sig figs. I think I might have too many. So looks like we just need 2. So I'm going to take off that. So 1, 2 significant figures. So the velocity of those cars after impact is 7.7 meters per second. Now here's always a good check to make sure you did the problem correctly. All right, your final velocity after the collision is always going to be in between the two initial velocities. What I mean by that is, car 1 was going 15 meters per second. When car 1 hits the parked car, car 1 is transferring some of that momentum to car 2. So car 1 is going to slow down, right? He went from 15 meters per second down to 7.7 when the collision happened. Car 2, their velocity increased from 0 up to 7.7. So this final velocity should always be between the two initial velocities of the objects, because one is going to slow down upon impact and the other is going to speed up upon impact. So it should always be in between because you need momentum to be conserved. And since this number is between the two, I can safely say that I did the problem correctly. So this problem is a follow-up on the two cars colliding and sticking together. Okay, so we're going to use the information from the last problem shown to solve. So what I'm going to do to the side here is write all the knowns and unknowns from this problem, but then from the previous one as well. So we have car 1, mass was 1750, their velocity was 15. And then the crunch time, so the time was 0.10 seconds. Okay, so this is the mass of the first car. This was the velocity of the first car before the collision. And then the crunch time when they hit was 0.1 seconds. All right. What we solved for in the last problem was the final velocity. So this was after the collision. Okay, and that was 7.7 meters per second in the previous problem. So I'm just going to focus on the first car, this part here. What is the impulse and force on the first car? Okay, so this is similar to that T-ball problem that we did. So when we're looking at impulse, remember impulse is the change in momentum. So change in anything is always final minus initial. So that's how we got this equation on our equations sheet, the MVF minus MVI, because that's the final momentum minus the initial momentum. Momentum being mass times velocity. Okay, so to calculate the impulse, we're going to use this equation for car 1. The mass of car 1 is 1750. Final velocity, so this is after the collision. So after the collision, we calculated in the previous problem that they were going, both cars were going 7.7 meters per second. Okay, we're going to subtract its initial. So the mass of the car was 1750. The initial velocity of car 1 was 15. Remember, that car slowed down upon impact. It went from 15 down to 7.7. So calculating this, we have 1750 times 7.7. We're going to subtract 1750 times 15. And I'm getting a negative number here. Okay, and I'm going to round it up to two significant figures. I'm getting negative 13,000 kilograms times meters per second. Mass in kilograms, velocity meters per second. Now remember when we calculated force in the last problem, with the t-ball, we used this equation and rearranged it. So to rearrange, we divide by t to get rid of t. Whatever we do to one side, we have to do to the other. So it becomes force is equal to impulse over time. So I'm going to take that impulse, that negative 13,000, divide it by the time, the crunch time, how long the cars were in contact, a fraction of a second. I'm going to get 130,000. Units on this are newtons. Okay, so what I'm trying to show by doing this calculation, and it's a negative, is that impulse and force always comes in action-reaction pairs. What that means is car 1's impulse is going to be negative. When I calculate cars 2 impulse and cars 2 force, it should be positive and it should be of a similar magnitude. All right? So let's look at car 2 over here. Let's calculate it and compare. All right, so for car 2, do this, and do it in a different color so we're not getting confused. So the mass of car 2 from the previous problem was 1650. The velocity of car 2, this is its initial velocity before the collision happened, was 0, right? It was stopped. It was parked. Its final velocity is the same as car 1 because when they collided, they stuck together, so they were one object going at the same speed. So that's why these are the same. And then the crunch time is also going to be the same. So calculating impulse, I'm using the same equation that's over here, but I'm plugging in cars 2 information. So the mass of car 2, 1650. The velocity of car 2, the final velocity, it was the same as car 1 because they're stuck together, so it's 7.7. I'm going to subtract that from the initial. Now the initial velocity, 0 because it was parked. 1650 times 0 is 0. So calculating the impulse, for car 2, I get 1650 times 7.7. And what do you know? When I round it up, I get positive 13,000. So the impulse between car 1 and car 2 in the collision are equal in magnitude because they're both 13,000, but opposite in direction. Okay, because one car 1, is slowing down upon impact, and the other car 2, is speeding up upon impact. So the momentum is being transferred equally and opposite. Now let's look at the forces. So I have negative down here for car 1. I got negative 130,000 newtons. So what do you expect the force on car 2 to be? Because forces also have equal and opposite action-reaction pairs. So I'm going to use my already rearranged equation that I rearranged over here and just plug in my numbers. So my impulse is 13,000. That's what I just calculated for car 2. I'm going to divide it by my time, and I get positive 130,000. Units are newtons. So car 2, the force on car 2 is positive 130,000. Car 1, negative 130,000. So opposite and equal. We just proved the conservation of momentum. We have another collision problem where we have two speedboats or two boats colliding into each other. So the first boat is traveling east and it's rear-ending another boat also traveling in the same direction. Okay, we're going to be calculating the final velocity once again, and since it's not quite clear, they specifically said that it's an inelastic collision, so we know which equation we're going to be using. Okay, so let's start by converting if necessary. Looking at all the numbers present, I got kilograms, I got meters per second, meter per second, that all looks good. So let's do our knowns and unknowns. So I have a mass here. I'm going to call that speedboat 1, 680 kilograms. So I continue reading, that speedboat is going at a speed or at a velocity of 15 meters per second. So that's going to be my V sub 1. So whenever we have a collision problem, it's between two objects. So we're always going to have M1V1 and M2V2. Okay, so here's my first boat, their mass, their velocity. Let's look at the second object, also a boat. So the mass of the second object is 560 kilograms. They are going a velocity of 5, so a little bit slower. What we're looking to solve for then is the velocity after the collision. And remember, when we calculate this, what's going to happen is the first boat going faster, when it collides with the second boat, it's going to slow down, right? Running into that second boat, it's going to slow down, it's going to transfer some of its momentum, and then that second boat's going to speed up. So our final velocity should be somewhere between 5 meters per second and 15 meters per second. So that's a check we're going to do at the end to make sure that we did the problem correctly. All right, so inelastic collision. So we're using the M1V1 plus M2V2 is equal to M1 plus M2VF. Now you'll notice pretty much every time you use this equation, you're going to be solving for the final velocity. So in order to solve for the final velocity, you need to get rid of this M1 plus M2. So to do that, you're going to divide. Whatever you do to one side of the equation, you have to do to the other. Cancels out on the right side, making it M1V1 plus M2V2, and all of that divided by M1 plus M2. Once again, noting this bottom portion needs to be in parentheses in your calculator so that it does the addition before the division. So let's plug in. So mass of the first boat is 680 multiplied by velocity 15. I'm going to add that to the mass of the second boat, 560, and this time it is in motion, right? It's going 5 meters per second. So it does have momentum. We're going to divide that now by the addition of the two masses. So 680 for the first and 560 for the second. So we have 680 times 15. I'm going to add that to 560 times 5. And divide that whole thing by 680 plus 560. How many sig figs am I looking at? 2? So I have 10.4. So it's just going to be 10 with a decimal so that that 0 counts. And it's a velocity, so my units are meters per second. Okay, so now here goes my check. Is it between 15 and 5? Yes, it is. Actually, right in between at 10. So some of this velocity, some of this momentum from the first speedboat was transferred to the second speedboat, causing speedboat 1 to slow down, speedboat 2 to speed up. Right? If you get rear-ended, your car is going to speed up a little bit. If you're the one rear-ending someone, your car is going to slow down a little bit. So